Okay, and then I will share the screen. Yeah, so last week we spent a lot of time trying to study this video about the scope of this event. So I think from last week's invitational, you have got a rough idea of what questions they might ask. So let's try to review these slides again and see if we can have a deeper understanding of all these things. Okay. So if you recall last week invitational, there are some questions of about the constellation recognition. So basically, you are supposed to remember the shape of all the constellations. So what I would recommend you is that you try to find all the 12 constellations that is for the deep sky object and try to memorize it. At least you can make a very small sketch on your cheat sheet, and in that way you can compare and recognize what the image is. So for example, the aquila, so you can see that it is an eagle, right? So it has a wing and it has a head, and it's pretty easy to recognize. And also for Canis major, so it's a dog, right? It's a big dog. So you know that there is a head here, and there is a series that is at the neck, and it has its front foot and the legs and the tail. So try to make a sketch of the constellation yourself, and so that you can make a very easy recognition. You can make a match yourself, okay? So we will go over this one by one. And besides, I think there is another question there asking if what constellation you cannot see in the northern hemisphere, right?
Right.
So let's try to solve this. So I think that is depend on how to find the constellations that are not be seen in the northern hemisphere. So because basically the idea is that the sky, the Earth is rotating around the sun, right, in a specific angle. And what you will see is that the sky is rotating, and in the north atmosphere, in the northern hemisphere, that you can only see this part, the upper part of the sphere, right? Because you can imagine that the whole constellation, all the stars around you are in a sphere. So it is rotating around you, but it is rotating very close to a specific point. So that point is the Polaris, right? So you know that it does not move. So we can find, for example, yeah. So you can find a star chart, right? So this star, you know that there is a Polaris here. So that is the North Star, and it does not move. So all the things will rotate around that point. So that is the northern atmosphere, right? So, you know that any constellation very close to the Polaris, it is very easily can be seen in the northern hemisphere. But any constellation that is very far away from the Polaris, can only be seen in the southern hemisphere. So we can take a look. So how they are distributed. So for example, this is the, yeah. So you can take a look at these and see how they are located. Yeah. Yeah. Yeah, so that is the basic idea. Yeah, I think this is the tutorial for finding the northern hemisphere and the southeastern sky, northern sky, western sky, etc. Yeah, but the most of, I think the most basic idea is that you can find the Polaris, and everything is rotating around it. And based on that, you can have some idea of how to, yeah. So this is the Polaris, right? So then everything is rotating around it. That is why you see a star track. So you see that the star rotating around the Polaris, and that is how it formed. Okay. I'll copy the link over here. Oh, night sky. Okay, so this is for constellation. Then let's go into the deep sky object, right? The deep sky object can be classified into three types. Number one is stars and the star systems, and the stellar remnant and the others. So star means I think if you are very familiar with stellar evolution, so you have a main sequence here, right? So star are basically different kinds of stages of all these stars, and the stellar remnant is usually when the star has evolved from the main sequence, and that is basically the post-main sequence stage. Then, for example, the supernova. So that would be the post-main sequence stage. And also
So you're fusing hydrogen to helium.
you said what?
I thought main sequence was when you fused hydrogen into helium instead of like when it's just fusing stuff.
Right.
So a red giant would still count as a star.
It's a star. Yeah, it is still a star. But there are other kind of nuclear synthesis happening inside. Yeah. Okay. So you can take a look here. So this is a very brief evolution diagram. So in the very beginning, that in the main sequence star, you have the hydrogen burning core, and all the hydrogens are burning, and they are, because it's super high temperature and super high density, super high pressure. So you have a fusion happening inside the core, and the hydrogens are collecting with each others and form helium. And this is nuclear synthesis. So it will keep evolving and evolving until the main sequence start become a red giant. So red giant is that when the helium began to burn. So in the very outside, so that is hydrogen. It is still hydrogen that is burning, but it forms a shell. In the very center, you have a helium core and no thermonuclear reaction. So the helium is not reacting yet. So it's not burning. So you can imagine that the core gets bigger and bigger. So so what is the difference between the main sequence and the red giant? Can anyone answer this question? What is the difference in their core? Can you answer?
I know.
Then what is it?
So the first one, main sequences are when a star is burning hydrogen in its core, and the red giant is when it is burning stuff that is heavier than hydrogen,
No.
mainly helium.
Look again. It says it had a helium core, but no thermonuclear reactions. So it's not burning.
That's when the helium flash begins. Well,
Yeah, when helium flash happens, it begins the thermonuclear reaction of helium. But in red giant, the helium core does not burn.
it still
Okay.
burns over here.
Yeah. So that is when the red giant after helium burning begins. Yeah. In the very beginning. So that comes helium flash. Yeah. So that is a hydrogen burning shell plus a helium burning core. Yeah. So this is the evolution. Okay. And then you have a type 1 and a type 2 supernova. So this is very, very important. So I hope you can make some notes yourself by visiting Wikipedia. So I think the most fundamental difference between type 1 supernova and type 2 supernova are the different physical mechanisms that make them explode. So do you know how a star can explode? How it can explode? Any idea? So when the star is big enough and it had a huge mass, so that mass is greater than 1.4 solar mass, and you have huge amount of gas, and you do not have enough pressure, then it will collide, and this collide will release energy and heat the gas up, and after that it will explode. So that comes the supernova. So people have known supernova for a long time, so since almost 1,000 years ago. But people recently realized that there are two types. So type 1 supernova is formed in a binary star system. So type 1 supernova. And the type 1 supernova can be divided into different subcategories. And the most famous one is type 1A supernova. So that is when you have a binary system, and one of them is a white dwarf, and it will form a dwarf. It will form a planetary nebula here. So do you have a two star system rotating each other? And then one of them is white dwarf, and it's pretty quiet. So if nothing happens, the white dwarf will not evolve. So it will just emit light and gradually die. So that is white dwarf. But since it has a companion, and the companion, when it evolves to a red giant stage, so you see here, so in the very beginning, it is main sequence. when it evolves into red giant, then it expand. So when it expands, some of the gas will be accreted, which means that extracted and pulled towards the white dwarf. So the white dwarf is in the center, and all the gas from the red giant is accreted to be very close to the white dwarf. So the consequence is that first it forms accretion disk because it has angular momentum. So if you do not lose the angular momentum, the material will keep rotating instead of falling into the white dwarf. So it forms accretion disk. And meanwhile, the accretion disk will emit energy. So because it is very dense and it had frictions inside, so it will release energy and it will remove the angular momentum away from the gas. And the gas falls into the star, into the white dwarf, and the white dwarf will grow. So that is what is happening here. And so the white dwarf is not big enough, right? So it will not explode. But when it accrete gas over and over again until its mass is bigger than 1.4 solar mass. So what would happen is that it is so massive, right? So it will collide. And the collide, it will collapse. And the collapse will result in he will release a significant amount of energy and it will detonation of the whole system. Yeah. So after type 1A supernova explode, basically nothing is left.
Except for the companion red giant.
Right, right. The companion will not be so much impacted. It will still be there. But the white dwarf, after the explosion, basically nothing is left. So all the things are released. So this is the most important factors that can enrich the gas. Because previously all the gas are hydrogen, right? So it's very, very clean. And there are no metal. Metal means anything that is heavier than helium. Sorry, not helium, hydrogen. So helium is also, you can call it a metal. So in the type 1 supernova, you have all the heavy element. So everything you know from in the period table, so they are formed in these over here, including gold. So all your gold are from supernova explosion. So yeah. Christopher, you have any question?
No.
Okay. Okay. So type 1 supernova. So it forms by accretion of the white dwarf. Okay. And type 2 supernova. So it is different. It is not in the binary system. It had only one star. So it is a normal star fusion. So you can see here in the very outskirt of the star, it is hydrogen. And in the core, it is helium and carbon. And when the star evolves to later stage, the central becomes iron. So basically iron. So this is the iron core. Anyone knows why it is iron? Why it is not something more heavier? Any volunteer?
Because the iron, when it fuses, it does not create any energy. So when it becomes iron, basically the core can't emit any energy to keep the outer layers from like collapsing in. So and because of that, the stuff outside of the core, because of all the gravity, just boom goes like that, and then it explodes
Yeah,
with a
yeah.
ginormous shockwave.
Right, right. So
And they're releasing a lot of energy in the process. Like in that split second, it creates very heavy elements all the way up to uranium.
yeah, very good. So when it reach iron, so that is about 60, the nuclear synthesis, the reaction will not emit so much energy. So because you need energy to create a fusion, then it will release energy. And for hydrogen, you release more energies than you absorb. But in iron, this reaction consumes energy instead of emitting energy. So that is why it stops. So after all the outer shells have burned, then it is basically a core rebound, right? So the core will implode. So it will first collapse, implode, and then rebound, and then explode. So that is the type 2 supernova. So type 2 supernovas, they are very different masses. So it could be very big, right? Like OB stars, right? So it's very bright and big and evolve very quickly, and then it form a type 2 supernova. So that is yeah, that is type 2 supernova. And the explosion is not that violent, so it will have some remnant core inside. So that is how it forms. And the remnant core, do you know what it is? Any
Apart from
idea?
me,
Sorry?
I know.
Yeah, so probably neutron stars. In most of the cases, it should be neutron stars because it cannot, because it should be big enough to form a type 2 supernova. And in that case, the central core is pretty big. Yeah.
Or it will turn into a black hole.
Yeah.
With if the star was 25 solar masses or larger.
Yeah, right.
And
The
then 8
initial
to
mass.
25, the initial mass, if it was 8 to 25 solar masses, it would be a neutron star. And then you have to be 8 solar masses to even have a supernova, unless it's a type 1 supernova.
Yeah. Okay. Sounds good. Yeah. Okay. So what would happen? What would be like the light curve for type 1 and type 2 supernova? So we can take a look. I think it's somewhere here. If I can't find it, we can search it online. This is one light curve. So this is a supernova 1987. So its light curve is something like this. It first becomes very bright, and then the light began to fade. So that is the supernova. But from this, it's probably not a supernova 1A. So it's a type 2 supernova. So let's take a look. What would be a type 1A supernova light curve look like? It's different from this one. Type 1A supernova light curve. Yeah, so you can see the difference here. So this is a very brief sketch. So type 1 is that you have a peak, then it just drops continuously. Right? Type 2 is different. So type 2 is it explode and then it plateaued. and after the plateau, it drops again. So there are some physical models behind it, and we will not go into that detail here. But the point is that for type 1 supernova, the light curve is pretty well modeled, and by a rise and then a decay. Yeah, no plateau. The plateau is only in type 2. And the one very important feature of type 1A supernova. So type 1A supernova is used as a standard candle. So cosmology, cosmodic, right? Cosmic standard candle. Sorry, cosmic standard candle, because it has the exact mass when it explodes. Because you no matter how big or how small the white dwarf is, so it will keep accreting gas around it, right? So it will keep growing until it reach that limit, and when you reach that limit, it explode. So that is why we use it as a standard candle, because it's the same mass and the same luminosity. So you, as long as you can measure the peak luminosity, then you know, and you can calculate, well, it is supposed to be a specific luminosity, and now I see it is apparent magnitude, then you can make a conversion. Okay. Okay, so since we are talking about the standard candle, then let's talk a little bit more about apparent magnitude and absolute magnitude. Apparent magnitude versus absolute magnitude. So there is an easy equation here. Formula. Let's find the formula. Yeah. Okay. Can anyone tell me what is apparent magnitude and what is absolute magnitude? Any volunteer? No? Okay. So I encourage you, all of you, to try to understand it. This is basically how we measure the how bright a star is. The apparent magnitude is basically how bright a star is when you see it. Okay, but since when you see it, so it depends on the distance. When it is very close, you see that, well, it is very bright, right? And when it is very far away, then it appears to be fainter. So that is apparent magnitude. And the absolute magnitude is that we assume we put the star to be a specific distance. So what is that distance? So that would be let's see. Absolute magnitude distance. So that is 10 parsec. Okay, so 1 parsec is 3.26 light year. So 10 PC is 32.6 light year. So the absolute magnitude means that if you put a star at 10 parsec away from you, right? How bright it is. So that is the absolute magnitude. Okay, got it? 10 parsec. 10 parsec, that is 32.6 light year. When you put a star at 10 parsecs, how bright it is? Okay, so that is the absolute magnitude. And the apparent magnitude, that is the small m here, that is it equals to the absolute magnitude, that is the big M, minus 5 plus 5 log d. So the d is the distance between you and the star. Okay, so that is the relationship here. So in the invitational, you have something like this, right? So what would be, so if you put if the magnitude changed by like 2 mag, so that means the difference in m is 2. So how different is the distance? So that is the relationship here. So let's make a very simple calculations. So if the distance, is the d is the distance measured in PC, and the log function, it is 10 based. So if, for example, if d equals to 10, then log d equals to 1. You got it? So everyone knows the log.
What is that supposed to be?
Sorry,
What is log supposed to be?
you don't know that.
No.
Okay.
The inverse of x.
The inverse of 10. So let me try to explain it. So
What's the base 10 log function?
what?
What's the base 10 log function?
Base 10 means how to explain it? So do you know the power?
Yeah.
So you have like 10 to the power of 2 equals to 100, right? And if you do 10 base the log for 100, it becomes 2. You got it? Because it's 10 to the power of 2 equals, and then you have a log of that. Then it becomes 2.
Oh, okay.
Get the point? So that is the power. Okay. So the log is to help you get the power.
Okay.
That's a 10 base the log. Okay. So look at this formula. So if a star is at 10 parsec, then the log 10 becomes 1, right? Because it is 10 to the power of 1. So this becomes 1. And 1 multiplied by 5 equals to 5, and 5 minus 5 equals to 0. So that becomes m, little m minus big M equals to 0. So that means m equals to m. So that tells you, if you put a star at 10 parsec away from you, you have the absolute magnitude, right?
Okay.
Okay, let's assume that you have the distance to be 100. What would it be? How big the magnitude change would be? The d equals to 100 here. 10 times further. Any volunteer? So if you put a star at 100 parsec, how the apparent magnitude would be? Okay, let's make a calculation here. So the d equals to 100, right? And the log d equals to 2. Okay, and 5 multiplied by 2 equals to 10, and the 10 minus 5 equals to 5. So when you have a star that is 10 times further, you have the magnitude 5 to be minus, to be bigger by 5. Because in a magnitude system, bigger number means fainter. So that is reversed. Okay, so if you have the 10 times bigger difference, so that you have a minus 5. You have 5 plus in magnitude. Okay, so try to record this formula and use that when you see any questions related to this. Okay. Okay, that is standard candle. You need to know the apparent magnitude and the absolute magnitude. And our next question would naturally be, what is the, okay, so what is the absolute magnitude of type 1A supernova? Right. So supernovas are, so the magnitude is about minus 19.5. So that's a good number. If you can remember that, then that would be great. So the absolute magnitude is minus 19.5. So all type 1 supernovas have that absolute magnitude. So let's assume that we have a, yeah, that's the big M here, right? So that is the big M, minus 19.5. So let's assume it is at 100 parsec. So what would be the apparent magnitude? Christopher, can you give it a try? So if D equals to 100, what would be the type 1A supernova apparent magnitude? Do you want to give it a try, Christopher?
45?
40.
No, like so like the log of 100 base 2.
Yeah,
that's
log
like-
equals to 2.
Yeah, so it's 5 times 10, which is 50, and minus 5, which is 45.
This is 10, right?
Yeah.
Minus 5 equals to, this is minus 5.
Oh.
Yeah.
Yeah.
Yeah, so 10 minus 5 equals to 5, right?
Mm-hmm.
And then you plus M, big M. Big M is minus 19.5. So what will be the number?
Negative 9.5.
Negative 14.5. Got it?
Right.
Yeah. And that means plus 5, right? So 19.5 plus 5. So that's
Yeah.
0.5. Okay. So if you have a type 1A supernova that is 100 parsec from you, then its apparent magnitude should be 14.5. Okay, got it. Okay, good. So we did some math. Okay, so that is for standard candle. Okay, let's go over some of the objects for the next 15 minutes. I think, did we go over this last time? I think we did, right? So Yeah, I want you to remember, at least make some notes in your cheat sheet. So what kind of object is this object? Is it a stellar remnant or a star? And what type of stars or what type of stellar remnant it is, right? For example, the House-Taylor pulsar. So it is in Aquila, and it is a stellar remnant, and it is a binary pulsar consisting of a neutron star and a pulsar, and it's orbiting around each other. So it rotates faster and faster because it loses energies, but when it's very close to each other, it rotates very fast. And House and Taylor, they are two professors, and they won Nobel Prize. Yeah, so this is for Aquila. Yeah, and next is the Canis Major. That is the big dog, right? The big dog that we talked about earlier. And then this is a A-type star. Can someone recall the main sequence number? Can someone give it a try? Nicholas, can you give it a try?
I'm sorry, could you repeat that? I did not hear what
We
you
have
said.
a sequence. So we have a sequence of main sequence stars.
Yeah,
Repeat that sequence.
I'm not sure the sequence, I'm sorry.
Yeah, okay. Let me show you something here. So this,
Thank you so much.
yeah, so this is the sequence. This is the sequence. So O, B, A, F, G, K, M.
OPAFGKM.
So that is the sequence.
Thank you so much. I did not catch that earlier.
Okay, so great that you learned something. Okay, yeah, so that is the main sequence.
There's a quick way to remember that too.
Yeah, so you know that if it's a A-type star, so where it is, so where it is located. So A star is here, right? So A is here. And it is a A-type star, means that it is a main sequence. A-type star. So its absolute magnitude should be something around like a positive 2 here. So that means it is brighter than our sun. Our sun is a G star here. So its absolute magnitude is a positive 5. So G star is here. That is our sun. And A star is brighter. Yeah. Yes, so you see that on the right, you see the luminosity, and the sun equals to 1, right? So that is 1 here. So you know that G star as our sun is over here. Yeah, A star is brighter and hotter. Okay, so it's an A-type star that is Sirius A, and the white dwarf, Sirius B. So white dwarf, where it is on the HR diagram? Let's take a look. So the white dwarf should be here at the lower down corner of the HR diagram. So that means it is very hot because the structure type, the structure class is basically temperature. So you can see here that when it's very hot, it's like 30,000 K. And when it's very cool, it's still like 3,000 K. So it's order of magnitude dynamic range in the temperature. And for O star, you have 30,000 K, and the white dwarf is in this range. So it's about like 10,000 K, right? But meanwhile, it is very faint. So it's hot and very faint. So it's hot, so it is white. People call it white dwarf because you see it's very white. Yeah, the light is white. So how to produce white light? You cannot produce white light using a light bulb. So it needs to be very high temperature to create a white light. Get it? Okay, so white dwarf is here. So it has a very high temperature and a very low luminosity. Low luminosity. How low? It's 0.01 solar luminosity. So 100 white dwarf combined together equals to 1 star, right? So you can imagine how faint it is. So 100 white dwarf, you put them in the same location, then it appears to be the brightness of the star of the sun. So that is how faint it is. It's 100 times fainter than the sun. Got it? Okay. Okay, so you have some deeper understanding of white dwarf, and then you have some understanding of A-type star, and you are supposed to memorize some of the basics here. Like the Sirius A is the brightest star in the night sky, and has been used as the basis for navigation because it is the brightest, and the calendar setting across history. And the Sirius B is highly starred and the second white dwarf ever discovered. Okay, so it is in the major Canis Major. So this is the real sky chart, right? So can you recognize it? It is very bright, right? So you know that the brightest thing is the color, the neck of the dog. So it is here. It should be this one, right? What?
It's supposed to be like a head over here, and
Where's
then
the head?
like I don't know. I don't see any very
Yeah,
bright
this,
stuff.
this should be the tail. And there are 3 stars over here. Where is the 3 stars? It should be these 3 stars. Let's see. Yeah, the 3 stars are pointing at the brightest star. Right. Okay, the 3 stars pointing at the brightest star, and there is a triangle in
But that's very
the left side, right? Okay, so pointing at on the left side. Yeah. Okay. Okay, next object is Cassiopeia A, and it is in Cassiopeia. So what does Cassiopeia mean? Cassiopeia means the seated queen. So it is a W. It's a W shape, so it's very easy to be recognized. So it contains Cassiopeia A, and it is the strongest radio source. So what is a radio source? So radio is literally means the radio you are using on your car or using a carry-on radio, or someone you use to walkie-talkie, right? So that is radio. And if you want to detect the radio signal from the sky, you need a huge disk. So just like the disk that you see around you to receive signal from satellite and receive signals from towers for TVs, etc. Yeah, so that is radio. And the radio has a feature. So radio wavelength is pretty long. It's usually a few centimeters. And the very famous radio wavelength would be 21 centimeter hydrogen. So that is a neutral hydrogen line, 21 centimeter. So you know that, well, 21 centimeter is about this long, right? So the wavelength for radio is about this long. So you can imagine that all the different radio waves around you are vibrating and propagating along. Yeah, it's interesting, and it can easily circumvent you. And if there is a building there, the radio signal can can walk around it and propagate continually. Yeah. That's interesting. Yeah, so this is a type 2b supernova. So it has a weak hydrogen line because it has a very weak hydrogen shell around it. So can someone recall the light curve of type 2 supernova? So what's the difference between type 2 supernova light curve and the type 1a supernova light curve? Which one had a plateau?
Type 2.
Yeah, good job. Yeah, type 2 has a plateau, and type 1 does not have it. Yeah, type 1 just drops. Good job, Christopher. And the Cassiopeia A is the brightest extrasolar radial source in the night sky. So the brightest within our solar is, of course, the sun, right? And one of the most highly studied supernova remnant. So this is how it looks in different wavelengths. So all different colors means a different wavelength. So this is combined, the three colors combined, and this is
This is
argon
using
line.
argon.
Argon line. So this is one emission line, and this is 2.1 micron dust in feature. So this to detect the dust around the remnant. And
There's
this
silicon.
is silicon line. Yeah, silicon. Cool.
Silicon is basically glass.
Yeah, so you
Or
can
sand.
see that they are different, right? So in argon, you cannot see it inside the remnant in the very inner part. But for silicon line, it is very bright here. So that is related to the physical properties of all these ionized gas. Yeah. So you can make a model. You can make a model to model this emission line. Then you can know the structure. Yeah. Yeah. Let's move on to the next one. Where are we now? Yeah. So it's a W. Okay. Next is Myra, and it is in Cetus. Theta, it means the sea monster. So you can imagine that this is the head and this is the body, right? So it's a sea monster. And it contains Myra A and Myra B. And they are not very bright. Yeah. But what makes it special is that it is variable star. So Myra A is an A-type star, right? So again, it is an A-type star. So previously we saw that another A-type star here, that is Sirius A. So Sirius A is also an A-type star. And over here, Myra A is also an A-type star, and the other Myra B is a white dwarf. So white dwarf everywhere. So you can imagine what would happen if the Myra A had evolved into a red giant. What would happen? Any volunteers? Passive? Can you imagine what would happen if Myra A evolved into later stages? What would happen?
It might be like a type 1A supernova.
In my what?
A type 1A supernova.
Yeah, very good. Perfect. Yeah, it will become the first type of A-type star will evolve into a red giant, right? And all the gas is accreted onto the white dwarf, and the white dwarf will accumulate the mass, and when it accumulates enough mass, then it will explode and form a type 1A supernova. Yeah. Good job. Impressive. Yeah, and before that, Mira A is just an A-type star, but it is variable. Okay, so this is the variability curve. So you can see that the brightness, apparent magnitude. This is the apparent magnitude. It changes so much. Right? It changes all the way from 9 to 2. So that's a huge difference, because as I showed earlier in the formula, that you change the magnitude by 5. That means distance is 10 times further. All right, from 10 to 100. So that's 10 times further, make it drop 5. And this drops almost like 8, right? So that is maybe like a 50 times further. So that is how faint it is. So imagine. So can it be that it changes? So it changed so much because the distance changed? Of course, no, because it does not move in the sky, right? So you know that it's changed because the star is changing in some other parameters. Yeah. So it's a pulsating long period variable star, yeah, which is known as Miro variable. Okay, that's all for today. And we are going to have another invitational this Sunday. Oh, sorry, this Saturday. So be there, and I'll see you there. And let's try if we can do better this time. Okay. And now you know how to make the cheat sheet, right? So record all these important features of the deep sky objects, and yeah, make a record and make a better cheat sheet. Okay.